Um, let's talk about binomial distribution. So binomial distribution is a discrete distribution. Here n is the number of trials or your total number of iterations, x is the number of success, p would be probability of success, and q is probability of failure, which is 1 minus p. So this means that probability of p plus probability of q, that should be equal to 1. Okay, so if I want to if I have a coin and I toss it 20 times, right, what would be the probability of getting 5 heads? So here my n, which is total number of trials, would be 20. X is number of successes, means I want x as 5, so x is equal to 5 probability of getting head on a fair coin, right? That is 0.5, so p would be 0.5, and then 1 q, which is equal to 1 minus 0.5, that is equal to 0.5 also. So once I plug in the values here, I'm gonna get 1.4%. That's my answer. So probability of getting 5 heads, if I toss a coin 20 times, that is 1.4%. um, Example number 2 could be, suppose the probability of purchasing a defective part is zero point 0.3, right? So here my p would be 0.3. What is the probability that 7 defective parts? So here x is 7 in a batch of 20 parts. So n here, which is my total number of trials, would be 20. So once I plug in the values, n is 20, x is 5, p is 0.3, then q is 1 minus the probability of p, right? So 1 minus 0.3 would be 0.7. So when I plug in the values, the answer comes out to be 16.42%. This means probability of getting 7 defective parts is 16.42%. This is a uniform distribution. It's a continuous distribution. The PDF is here. This is the PDF. Once you integrate it from minus infinity to x, uh, this is my CDF. You need to know that for when we are integrating it, we support this minus infinity by the lower bound of this distribution. So we are replacing actually minus infinity with a. Derivation of this is discussed, or it's part of another course, so we will just directly use the formula. Or if someone is interested in the derivation, then in inferential statistics class we are discussing in the CDF as well as the inverse CDF of that. Okay, so it's a continuous distribution example, and we are using a uniform distribution. So suppose that x is a random variable that represents the actual contents in ounces of 1 pound bag of coffee beans. You need to know that 1 pound is equal to 16 ounce. Right, the probability distribution function of x is given here, this one, and the lower limit is 15.5 and the upper limit is 17. So instead of minus infinity, I can use 15.5 and x here, which is 1 pound, so it's 16. So I plug in the value here, and because 1.5 is a constant, I just take it out of my integration, and the answer comes out to be 0.333. So the probability of a bag containing less than 16.0 ounce is 0.333. Such problems are extremely critical for quality control, because when customer is paying, then the customers won't be very happy if they know that they received a content less than what they paid for. So such continuous distributions could be used in quality control examples. Next is the normal distribution, extremely common, and basically it has got two parameters. One is mean and second is the standard deviation. So if if I know mean of a sample, and if I know the um, standard deviation or variance of a sample, then I can generate further samples from that normal distribution using Excel uh, variates or Excel tools. And there is a built-in formula. Norm in V is basically a built-in function in Excel. So some examples that follow a normal distribution: heights of people, size of things, produced by machines, error in measurement, blood pressure, and test scores. It should be so. If what my understanding is that if my sample size is more, right, then it's a very good idea to use normal distribution or standard normal distribution. But if my sample size is, I would say, less than 35, or a small sample size, then it's a very good idea to use T distribution. But if sample size is like around, let's say, 20,000, 10,000, then it's good to stick with normal distribution or standard normal distribution. So if you are using Excel, you don't need to transform you don't need to transform normal distribution to standard normal distribution. But if you are using tables, then it's a very good idea to transform normal distribution to standard normal distribution, because values are given for standard normal distribution in tables. So here regarding first sigma and plus minus 1 sigma, right? So what is the interpretation of that? That 68.26% of population will lie in that region. So let's say I'm saying the height of a population is 4.5. That's the mean value, right? So I would say, and 1 inch this is the standard deviation. So 4 feet 6 inches and 4 feet 4 inches, right? That's my lower bound and upper bound for first plus minus sigma, right? So 68.2% of people will fall in that. If I go to one more sigma, so plus minus 2 sigma, uh, that would be 4.4 feet 7 inches and 4 feet 3 inches, and 95.46% of the people will be in that height range. So that's basically the application of normal distribution, and it's a bell-shaped curve. So one side uh, symmetric, one side is basically the mirror of another side. So the standard deviation is a measure of how spread out numbers are, and this is what I just explained, that uh, what is plus minus 1 standard deviation, what is plus minus 2, and keep on going. So this is the PDF of a normal distribution is given, but it's not you cannot integrate it, right? So what they are doing, they are transforming it to standard normal distribution. And here mu is my mean value, a is my RV random variable, and here sigma